Let us look at another form of Gauss law. I did not want to discuss this, but as this keeps coming in many test series, and also once it was given in mains, so I want to discuss this. So the another form of Gauss law is del bar dot E bar equal to rho by epsilon naught. So this is electric field and this is the volume charge density. Okay. So let us see this. Let us see the derivation of this. Okay. So at in space at some x comma y comma z, let us take a cube. Okay, imaginary cube of very small length. So this is dx, this is dy, and this is dz. Okay, and let us calculate the electric flux. Suppose the electric field here, the x component of electric field here is Ex. Okay, so this is x plus dx, right? So here what will be the field? X plus dx. Okay, so what will be the flux in the x direction? Let us see the flux in x direction. Electric flux in x direction equal to, so what is the flux through this phase, tell me? Ex plus dx into dy into dz. That is Ex plus dx into dy into dz. So this is the flux at this phase. What is the flux at this phase? So flux is entering, right? Entering will be negative, minus electric field into this is dy into dz. Okay. So let us just simplify this. X plus dx minus Ex into dy dz. Okay. How can I write this? Tell me. I can write this as dou E by dou x into dx dy dz. So the change in E with respect to x into dx into dy into dz. Okay. So I can also write this as dou E by dou x times dv. Okay. See, dx into dy into dz is a volume of this cuboid. This is a cuboid, volume of this cuboid. So we have got the flux in x direction. By symmetry, what can we say? The flux in y direction, dou E by dou y into dv. So what is the total flux through this cube? Tell me. Total flux through cube equal to dou E by dou x. I'll just take dv common, plus dou E by dou y plus dou E by dou z times dv. Okay, and this total flux from Gauss law is what? Equal to q enclosed. Let us say, because we are taking a small volume, this is dq divided by epsilon naught. Suppose there was some charge inside this which is dq equal to dq by epsilon naught. Now how can I write this? Tell me. I can write this as del bar dot E bar. Okay, this whole thing, this del bar is dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. And what is this E bar? Ex I cap plus Ey j cap plus Ez k cap. Okay. So this is basically this I've written here into dv equal to dq. I can write what? dq I can write this as volume charge density into dv. Okay, whatever is the volume charge density here into the volume is this by epsilon. So I can cancel out these both. I can so finally I'll get del bar dot e bar equal to rho divided by epsilon. Okay, so apart from this form, that is integral e bar dot ds bar equal to q enclosed by epsilon naught. Remember this also, del bar dot e bar equal to rho by epsilon naught. Let us move on to the next question, and this question is from Fiji AITS paper. Okay, so it's given this is electric field in space, and consider a cylinder. Okay, and let us see what are the options. The electric flux to the lower circular base is 0. Okay, so you see the electric field here, E naught xi cap plus yj cap plus z k cap. The lower surface which is there, it sits on the xy plane. Okay, so what is this z here? Z is 0. So that means the electric field is E naught xi cap plus yj cap. That means electric field, if you see the direction, it points along like this. Okay, no line cuts this surface, the base surface. So we can say the electric flux through the lower circular base is 0. Next, the electric flux to the upper circular top is pi a square h. What is the electric flux to the upper circular top? So here let us say this is E. Okay, and some area dA let us take here. Obviously the direction of area will be this side. So let us find what is the flux. So d phi equal to EDA. Okay, so that is this E naught into xi cap plus yj cap plus zk cap dot. The direction is along k cap. Okay, so k cap. So what is, see, for all the points on the top surface, z is equal to h. So I can just write d phi equal to E naught h d. Okay, and just integrate this. What is this integral dA? Tell me, or adding all the areas here, that will be the area of this circle here. So this will be through the upper face equal to pi a square E naught into h. Okay, so that is what he has given. So this is also the correct option. Next, the electric flux through the lateral surface. So through this lateral surface, what is the electric flux? So now we can do this by two methods. One is direct integration we can do, or the second is we can use the another form of Gauss law. So we'll do both. Okay, so first we will use the direct integration. This is E. See, at any point you can say that E is radial. So if this is the origin, radial vector is like this, no? So E is like in the radial direction. And area, let us say the slant area, no? So area will be like this, and this area will point outward. Okay. So what will this be? Tell me. D phi equal to E. We can just write down this E naught into xi cap plus yj cap plus zk cap dot. You see this area at every point, it is outwards like this area. So what will that be? Tell me. This is there is no k cap component, there is only x and y. So this will be, we can write this as, you see this area, we can write this as the magnitude is dA, and the direction is radially outward like this. So what is the vector which is outward? That is nothing but xi cap plus yj cap divided by a. This is a unit vector. Xi cap plus yj cap by the magnitude. Magnitude is a, which is the radius. Okay. So now let us move forward with this. D phi equal to E naught by a. Now this becomes x square plus y square into d. Okay. And what is this x square plus y square? You see here, x square plus y square is nothing but the radius. So directly I can write this as d phi equal to E naught by a, radius square, okay, a square into d. Okay, just cancel out these two, and what will, we can just integrate this. These two are constants, we can just integrate the area. Okay, so this comes out to be E naught a. See, if all this area integrate is nothing but the curved surface area. So what is the curved surface area? 2 pi r into h. So we get this flux as E naught 2 pi a square into h. Okay. So yes, this is also the electric flux through the lateral surfaces 2 pi a square into h. Okay. The total electric flux through the cylindrical surface. So what is the total electrical flux through the upper face plus this? So the total electrical flux will be 3 pi a square E naught into h. Okay, but he has given 4, so this is not the correct option. Now let us look at the second method. See, we have found this part, okay, the electric flux through the upper circular top. If we can find total flux, then we can also find the answer to this and the answer to the C part also. And so for finding the total flux, we'll use del bar dot E bar equal to rho divided by epsilon. This is another form of Gauss law that we have studied. Okay. So what will be del bar dot E bar? Dou E naught by dou x. So this will come out to be 3 E naught equal to rho by epsilon. So what does rho come out to be? Tell me. So anyways, our rho is a constant. So directly we can find charge in this cylinder. What will be charge inside the cylinder? So charge enclosed by cylinder equal to volume charge density into volume. So we get this as 3 E naught epsilon naught into volume is pi a square into h. Okay. So this is total charge. So what is the total flux? Charge enclosed by epsilon naught is a total flux. So we get this as 3 E naught pi a square into h. This is the total flux. Okay. So from this differential form, we can get what is the total flux. So this option we can say it is not correct, because we know the total flux and flux through the upper face. So through the curved face, the flux will be this minus this. So from there we can get it is 2 pi a square h E naught. So any method you can use. Either you can go for the integration method, or you can use the differential form and find the flux.